Hello everyone, this is video number 5 of chapter 4 of the lecture notes, and we're finally going to discuss here what is the link between group theory that we have been discussing in the last 4 videos and cryptography. So the goal of this video is to explain you how we can build a public key crypto system using groups, okay? If you remember from our lectures of chapter 2 and perhaps from the example that we discussed in chapter 3, the main ingredient that you need when you're building a public key crypto system is that of a trapdoor function. Okay, trapdoor function. That is really the crucial concept. And if you remember, a trapdoor function is a bijective function, which is very easy to compute in one direction, but the inverse function is very hard to compute for all practical purposes. Okay, if we were discussing RSA, for example, that we discussed in chapter 3, the trapdoor function that is behind the RSA crypto system is that we can multiply prime numbers. That's very easy to do, multiplying prime numbers. Prime numbers, that's an easy computation. Okay, and the problem that is very hard is the opposite direction, is finding the prime factorization of a given integer. Factorization. Hard, okay? And the whole RSA crypto system, its security is based on the fact that it's, for all practical purposes, impossible to find the prime factorization of very large integers, okay? And now what I'm going to explain you in this video is that, in fact, cyclic groups provide for a new trapdoor function. Trapdoor function, okay? So let us see what this trapdoor function is. So it's actually quite simple to understand. Suppose you have some cyclic group, okay? So let's call G the set of elements, delta the composition of the group. And suppose this is a cyclic group, okay? So let's take a cyclic group here. And since it's a cyclic group, it admits generators. That's the definition of a cyclic group. G is an element of the group that is a generator. So it means that you can build using only the powers of G. So G composed with G and G composed with G composed with G and so on. You can build all elements of the group G, okay? So given this, there is the following bijection. If you take on the one hand all the numbers, 1, 2, 3, until the cardinality of the group, so here, G, that's on the one hand side, and on the other hand, elements of G, there's a bijection between these two. And this bijection is the following. On the one hand side, on the left hand side, you have the number k, and you associate to this the element G to the power k. Okay, so that's the bijection. Now it turns out this bijection is a trapdoor function because one of the directions is very easy to compute and the other one is not. So the one that is easy to compute, let us write it here, easy, is from the left to the right. So if you give me a number, k, and I want to compute from this the number j to the power k, well, I can take a computer and I will do this very easily. What is hard to compute, on the other hand, is the opposite direction here. If you give me a number y, so y, an element of G, and you want to find which of small g will give the number y, well, this turns out to be very hard. Okay, so if you ask the question, which power here is giving me the number, the element y, this is very hard. Okay, so let me just show you an example first of this. An example, explicit example, where you can see that this is indeed the case. Okay, so let's take a real life example. We're going to take z over a very, well, not so big number actually, 99371 Z, okay? So we are working modulo 99,371, and we're using multiplication. So we're taking just all the non-zero elements of this. It turns out that this number is a prime number, okay? So that's our group. And I'm going to take as generator the number 139. Okay, so it could be an exercise for you to check that 139 is a generator of this group. Okay, so for example, I can ask the question, let us compute, first question, and one direction. You give me a number, let's say, let's take the year we are on, 2021, and let's compute 139 to the power 2021. Okay, that's one question. Second question is find x such that, and now let's take the same number, 2021 is produced as an output as a power of 139, okay? So which power of 139 will produce as an output 2021, okay? And let's just take a computer to do this calculation. So let me just share with you some number. Let's do this with Wolfram Alpha, but you can use any other means that you want. So first one that I was telling you to do is compute 139 to the power 2021, and we say the modulus 99371, and we ask the computer to do this. Okay, so it takes a second, 2 seconds, and it just gives me the result in very quickly, 75362. Okay, so that was easy to do. Okay, that's what I mean by easy. Now let's do the opposite. Let us try to ask the computer to solve the equation 2021 is equal to 139 to the power x modulus 99371. And let's see what happens. So now we just ask the computer. It tries to compute for a certain time. So you see already that it's taking much longer than the computation on the other direction. 3, 4 seconds, even 5, 6. And after a while, it just says, I'm sorry, standard computation, I'm able to solve this equation that you're doing. Okay, so that's a very simple and practical example where you see that it's very easy to compute the powers of 139 modulus 99371, and the opposite, just finding a certain result, is not so easy. Okay, so let me come back to the notes here. Good. So we saw, just check that this was easy to do and that this was not possible to do with the computer. Okay, so this problem, the problem that is hard here, the problem of solving the equation y equal j to the power x given y that is known, this is known as the discrete logarithm problem. Discrete logarithm problem. Okay, logarithm problem. And as I have just shown you, is a very hard problem to solve for just simple groups that you can take. Okay, so if you want the precise definition, it was, so this is taken from the lecture notes, the discrete logarithm problem. So what is it? You take a group that is cyclic, G with the operation delta. Okay, you take a small g that is a group generator, and you want to solve the equation y equals j to the power g to the power x, where the unknown is x and y is known. Okay, it's fixed for you. So here in this example, it was 2021. Okay, the solution, the x that is a solution of this equation, is denoted as logarithm in base j of y. Okay, so that's the discrete logarithm problem. Good. So maybe 1 or 2 remarks before we end up with this video. First is, why is this called a discrete logarithm problem? So let us discuss the terminology. Perhaps it's obvious to you, but it depends on how the logarithm was defined for you. For some people, that's the definition. So why is it the case that when we are doing this equation, we say that x is the logarithm in base g of y? Okay, For some people, that's the definition of what the logarithm is, but it depends on what you have done in your past. Okay, so just think what it happens in R. If we're doing this in R, the equation y equals j to the power x, well, if you want to solve this and isolate x, you apply logarithm on both sides, like the natural logarithm, and this is ln of y is equal to x ln of g, right? Which is the same as saying that x is ln of y over ln of g, and that is in fact the definition of logarithm in base g of y, okay? So by analogy with what happens in R, for any group, we will talk about x being the discrete logarithm of y in the base g, okay? So that's the first thing, terminology. The second point that is quite important, and let me just write this down in another color, is that in fact, the difficulty of the problem, the difficulty of the problem, of the discrete logarithm problem, depends on the choice of the group. On the choice of the group. Okay, and that is a very important remark. So not for any group that you take, this equation is going to be hard to solve. Okay, so I just gave you a first example. Example 1 was if the group that you take is, for example, z over, what did we took? 99371z with multiplication, right? So if that's the group, then the problem is hard. It's extremely hard, and it turns out to be as hard as the prime number decomposition. So it's a sub-exponentially hard problem if you know a little bit about complexity of algorithms, okay? However, if you take another group that we know, for example, if we take for group, let's say z over nz with addition, okay, which is a cyclic group, then the problem is in fact very easy to solve. And why is it that? Because the discrete logarithm problem is to solve this equation, right? So I give you y, I fix g, and I want to find for which, how many times should I compose g with itself, right? So x times here, x times, and how many times should I compose g with itself such that it produces y, okay? But if you notice, when we're doing addition, this is exactly the same as asking the question y equals g times x, right? And this is very easy to solve because the solution here is simply to say that y is x is equal to y times g minus 1, the inverse of g. So you see that for when the group is addition, the discrete logarithm problem, is equivalent as a problem to the computation of the inverse. Okay? Of inverse. And you know that that's very easy to do. This is very easy because this problem can be solved using the, for example, extended Euclidean algorithm. Any computer can do this. Okay, so what is important for you to keep in mind is that the discrete logarithm problem is sometimes hard, for example, when you use the multiplication group, but it's very easy when you use addition. And one of the goals that we will see in the future is that to find sophisticated groups in which the discrete logarithm problem becomes harder and harder to solve.